Yes, guys. So in the previous class, good morning everyone.
Good morning, sir.
Right. Ready with physics? Physics books. So in the previous session, we have discussed what concept we have discussed. Which chapter we are doing? EMI. EMI, electromagnetic induction. In this, we have discussed which one? Open your notebooks and tell me what we have discussed. Right hand palm rule in understanding what? Yes? This side? Right hand palm rule. For understanding what we have used right hand palm rule. Direction of induced EMF. So we have discussed about the motional EMF concept, and especially we have discussed how to find the motional EMF of a rotating rod. Motional EMF of a rotating rod. And to understand the direction of induced current, we used right hand palm rule, or you can say Fleming's right hand rule, right hand palm rule. Now, as part of that, we will see few more points. How to find the induced EMF of a rotating disc, and so how to find the energy or the power loss, power dissipated when a rod is moving on a rail, or in any case if you can say a rod is rotating. So in this case, how to find the work done in the process of moving the rod, or the loss of power or dissipation of power during the process. Briefly, then we will see one simple concept called eddy currents. What are eddy currents? There are no mathematical expressions on that. Simply what are eddy currents? Then we will see what is self-inductance of a material or of a current carrying coil. So first we will discuss how to find the EMF induced when a disc is rotating about a fixed axis in a magnetic field, external magnetic field. So if you consider a disc, it is a disc with center O and radius R. When it is rotating about an axis perpendicular to the plane, and if a magnetic field is also acting perpendicular to the plane, or you can say the axis is parallel to the direction of magnetic field, then you can say when it is rotating about this axis with an angular velocity omega, you can say some EMF will be induced in this. So the EMF, to find the induced EMF in this, we can treat this as identical to yes guys. So we can consider this as a combination of a number of spokes, and this very closely formed spokes. What is this meaning of the it is a combination of spokes is, if you have a spoke here it acts like, so just simply, there is no material here, there is a rim, and from the center a spoke is attached to this rim. Similarly, number of spokes are attached to the rim from the center. Are you following everyone? Then, when it is rotating in the magnetic field, external magnetic field, so already we have discussed how to find the EMF induced in a single wire or rod rotating in an external magnetic field. So this is a single wire, this is center, and this is so that its radius is r, and hence it is acting as length of the wire. Then EMF induces across this when it is rotating in this direction. What is the EMF induced? Or induced EMF in case of a rotating rod? This is a rod of length L, 0 and L. Then what is the EMF induced, and hence induced current in this? What is EMF induced? What's EMF induced? In the rod, rotating rod. LVB. Look into the notebook. What is the EMF induced in a rotating rod? Rotating rod. Did we discuss about induced EMF of a rotating rod? JE guys. So what is EMF induced in a rotating rod? B omega L square by 2. Right? In NEET we have not discussed. Then we will see briefly once again what is the EMF produced in a rotating rod. Then we will go ahead with this. EMF, or you can say motional EMF, motional EMF of a rotating rod. Rotating rod. To understand this, let us consider briefly there is a uniform magnetic field, external magnetic field, and having a strength B. Index should be. In this we have a rod of length L, which is fixed here at this end. Let us say this is O and this end is A. And this rod is rotating about this point in anti-clockwise direction. To find the EMF induced when it is rotating in the external magnetic field, you can say every part will be moving with velocity v, every part. So it is something like a wire moving with velocity v in external magnetic field B having length L. Then induced EMF is given by BLB. Right? If it is under linear motion, if a wire of length L is moving with velocity v in external magnetic field, induced EMF is given by E is equal to BLB. Right? Whereas when it is rotating, then if it is rotating with an angular velocity omega, to find the induced EMF, we have to consider one small element. We have to divide this into number of identical elements, smaller elements of length dx at a distance x, let us. When you say this is moving with velocity v perpendicular to its length and perpendicular to the magnetic field, in this small amount of EMF induces, it is given by dE. So E is BLV. So D is in the magnetic field D with the length dx. When it is moving with velocity v, the induced EMF produced in this small element is v dx v. Whereas the total EMF, if you want, and in terms of angular velocity, if you want this, if any particle moving in a circular motion, we know that the relation between linear velocity and angular velocity is v is equal to r omega. Again you can write, because v is equal to r omega, where r is radius of what is that? Circular path of the particle. This the radius is nothing but x. So you can say in this case v is equal to x omega. Right? Consider here. So you can write this as dE is equal to v is x omega. So you can write v omega x dx. So this is the small amount of EMF induced in this small element. Like this number of elements, identical elements are divided into. So the total EMF is E is equal to integral of dE, where this can be expressed as integral of b omega x dx, where when the element is going from here, x changes. X is the variable. From where to where it changes? From 0 to L it changes. So if you take this, then write it as x is equal to 0 to L, and these two will be constants. Only x will be the variable. So if you take this b omega out and if you integrate x dx, you get x square by 2. With the limit 0 to L, if you take, we get b omega L square by 2 will be the motional EMF induced in a rotating rod. Motional EMF of a rotating rod is given by b omega L square by 2. Right? When one rod or wire of length L is rotating. Okay. Now, as an application of this, or as an extension of this, if you consider, yes, have you copied this, everyone? Not done fast. Next, you have to copy simultaneously, guys. You have to habituate that. Okay, don't move, watch a movie like. Don't sit calmly. Right. Look, next. An application of this is, let us say an extension application. If you have a rim with center O and these kind of wires, if we attach like this, number of wires, then, so if the length of each wire is L, stop talking, listen, if length of each wire is L, then you can say across every wire, if the entire rim is rotating in the external magnetic field, then you can say, so every wire or this spoke, we can call them as spokes of the wheel, are rotating with an angular velocity omega. Here, the radius is nothing but length of each rim. Now we can say, as in this rim or in this spoke, in an EMF of E is equal to b omega L square by 2 induces. And this induced between these two ends. And it looks like all these first end of every wire is attached here, second end is attached to this rim, it acts like a conducting wire. So you can say all of these are parallel to one another. So in parallel combination, if you remember, if you recollect back, parallel combination of resistors. The EMF across parallel combination of number of resistors is same. So in case of a rim, with spokes, EMF induced across every spoke or wire should be same. EMF across every spoke should be same as they appear to be in parallel combination, as they are in parallel with one another. They are in parallel. Right? EMF across every spoke should be same as they are in parallel about these 2 points. So you can say in case of a rim with the spokes rotating with an angular velocity, potential EMF induced across every spoke is, therefore it is given by E is equal to what? B omega L square. If it is radius, we take it as R, then we can take R square by 2. And if you want to know which end is at higher potential and which end is at lower potential, we have to use Fleming's right hand rule or right hand palm rule. So if it is rotating, this point is moving up with a velocity v and magnetic field is into the plane, then you stretch the fingers of right hand into the plane and the thumb in the direction of velocity. Then, so the direction of palm will be at higher potential and the other will be at lower potential. So this will act like a battery with this higher potential, lower potential battery. So this will be at higher potential, this will be at lower potential. Is that clear? So when you have a single wire or number of wires in a ring also. The same thing you can consider this is number of cells. So each spoke will act like a cell with these polarities. So if each EMF is E, number of such spokes are connected in parallel, EMF across every spoke will be equal to E only. And that is given by this. The EMF, induced EMF is. Got it? Right. So now, this point we will use in the next concept called how to find the EMF induced in case of a rotating disc. Rotating disc. Let us see next here. The EMF induced in a rotating disc. EMF induced in a rotating disc. EMF induced in a rotating disc. If you consider a disc is nothing but a thin plate, okay, and with center O and radius R. That is the radius R. And it is placed in uniform magnetic field. EMF induced in a rotating disc in a magnetic field. So if we consider a line passing through the center and perpendicular to this plane, we consider this as an axis of rotation of the disc. If axis is perpendicular to the plane and in the it is parallel to the magnetic field, and if the disc is rotating like this in the anti-clockwise direction with angular velocity omega, we can consider this disc is a combination of number of spokes, very closely spaced spokes, yes, very closely spaced number of spokes. So whatever may be the number of spokes, irrespective of number of spokes, whether 4 spokes are there, 400 spokes are there, or 4000 spokes are there, potential difference across the center and rim of the disc, and hence this rim and hence this disc will be same. So this is analogous to the potential difference EMF developed across the spokes of a rim. It is analogous to the EMF induced across the ends of spokes of a rim. Is it clear, everyone? A wheel, you can say, not rim, a wheel. Right? So this you can recall as the rim part, and this is the spokes together with the rim is called wheel. So the induced EMF or EMF induced by rotating disc is same as the EMF induced across the spoke of a wheel. Okay, so you can see this here. EMF induced in a disc is equal to half B omega L square or R square. If that length of that rim is identical to radius of the disc. Simply you have to write one word here because the disc is treated as a wheel with number of closed spokes with the number of closely spaced spokes. Right? So that conceptual related point. No calculation is involved. That's it. Got it? So the EMF induced across each spoke of a wheel, a rim with spokes, or you can also call it as a wheel, or it is analogous to the disc. Both are same. Next we will see briefly. What is the power loss? Power loss or the work done in moving a wire on a rail in uniform magnetic field. So to understand that, let us consider this diagram which we have considered while deriving the expression for motion EMF. There is a pair of tracks or rods which are separated by a length L, so they are connected by a wire, you can say of length here. On this, another mobile wire is placed. You can take this as a PQ. It is this entire arrangement is placed in uniform magnetic field. Now, if you apply a force on this and if you are moving this with the velocity v to the right, we have discussed that EMF induces, if this length also should be L, so the EMF induces in this, that EMF is called motional EMF. And motional EMF is given by V, L, V. And what is the direction of this motional EMF? Means what are the polarities? You have to use right hand thumb rule according to it. Stretch the thumb in the direction of the last and the fingers in the direction of field. So the palm direction will be higher potential, this will be lower potential. So current will flow from higher to lower potential, means induced current will flow from Q to P in this case. Okay, fine. Now, as we have applied a force on this and we are moving this with the velocity v. But here you have to bring one more point that if this velocity is constant, if there is a force, means actually force is equal to mass and acceleration according to Newton's second law. So the velocity should not be constant, it should be increasing continuously. But we are telling that by applying the force we are moving this with the velocity, constant velocity. That means there should be another force which is balancing this so that net force becomes 0 and hence velocity will be constant. That force actually considered to be the magnetic force acting on this wire. Why magnetic force comes here is we have this magnetic field, external field, and when it is placed on this movable wire in contact with this rails and is moving, EMF induces and hence current also induces. So when the current induced current is flowing from Q to P, we can treat this as a current carrying wire in. Stop talking, concentrate here. Everyone is watching there. The current is induced in the wire and it is flowing from here to here. So we can treat this as a current carrying wire in uniform magnetic field. Current carrying wire in uniform magnetic field. Then we have to recollect back one of the concepts we have discussed in moving charges in magnetism. These are interrelated ones. So if you have not attended those classes, you have missed those, you will get confusion. So you have to go through and you have to recollect back those concepts also. So the magnetic force acting on a current carrying wire in uniform magnetic field is given by ILB or BIL. Do you remember this, everyone? Right. So this force acts in opposite direction. So if these two forces are equal in magnitude, then they are acting in opposite directions. That force will become zero, but still it is moving, means force is zero, acceleration is zero, but velocity is not zero. Acceleration is zero means change in velocity is zero. So means velocity is constant. This will be moving with constant velocity. In this process, of course, if you consider the external force applied, then what is the work done? Work done, if you want to find, work done is nothing but force into displacement. If it is displacing every time, then only EMF area changes, flux changes, and hence EMF induces. Got it? So you can say work done is nothing but this force into displacement or distance taken by this. This work done per unit time gives the work done per unit time. Work done per unit time by the external force. By external force is given as power. Work done per unit time. Nothing but energy per unit time. Right? So this power given or spent in moving the wire is nothing but force into velocity. Force into velocity. Do you understand? Force into velocity. This velocity can also write in terms of other related terms. Angular velocity. Here there is no angular velocity concept comes. If it is related with that, you can consider that what is the work done per unit time, or the power spent in rotating the wheel can be taken in this way. Force into angular velocity form also taken. What it? The same form. If you are asked to find the power dissipated in this process is given as P is equal to, P dissipated is equal to, in terms of induced current, then write it as I square R. If resistance in the coil is R. If the resistance in the coil is R. Class is up to 9:50, right? Yes. So here you can say the work done per unit time by external force in moving the wire or removable rod is force into velocity. Whereas the power dissipated in terms of induced current, if the entire this loop is having a resistance R, then you can write it as I square R, where R is the resistance of the loop. If you can take this as PQRS, loop PQRS. So here you know already induced current is nothing but where induced current is I is equal to induced EMF by resistance. Induced EMF by resistance. By substituting this, we will get the power. Got it? So these are few related terms you need to have an idea of. This you can also call it as energy consideration of motion EMF. Energy work done per unit time is energy. You can say power dissipated is nothing but energy per unit time. So you can say this is energy consideration. Energy consideration of motional EMF. Motional EMF. Okay. So these relations directly you may come across by doing the numericals. As I said, one small concept is there, eddy currents. No numerical related calculation part is involved. Only what are eddy currents you need to have an idea. Then you can try to work out some numerical based on all this. Okay. And inductance concept is left over. That means mutual self and mutual inductance part that we can cover in the next session. Okay, and so numericals related to all this. Again, tomorrow we will be having study hour, right? Tomorrow study hour time we will get to cover few more numericals. So we have, what is this? Motional EMF of what is that? Linear motion of the rod and rotating rod and related terms, and then what is that? Induced inductance. You can say self-inductance and mutual inductance part. There is applications of those are not there. Only the basic part of self and mutual inductance. So much is there about the applications of that. So that we will discuss in the next session, next week. Okay. Right. So this is briefly about the energy consideration of motion EMF. Right. So the work done, per unit time in moving the wire or in rotating the wire also. You can say rotating the wheel, and power dissipated per unit time is given in terms of induced current is given by this. In this case or in that case, it is applicable for both cases. Next, write down eddy currents. Subheading eddy currents. So eddy currents are nothing but induced currents, but these are special induced currents. Eddy currents. Eddy currents are nothing but induced currents. We have discussed in all this case about induced currents. Induced current is nothing but here induced EMF or motion EMF by resistance of the coil, resistance of the loop. Right? In the case of the rotating wheel also the same thing is applicable. Yes, man. Whereas eddy currents are nothing but if you have, instead of a wire, if you have a thick metallic disc, bulk metallic disc, bulk disc. If you consider a bulk disc will be having so much of it. We also call this as a flywheel. This is one of the examples where we will observe these eddy currents actually. So if you have a bulk metal rod or bulk metal, and if this is subjected to change in flux, so that is if you kept this in uniform magnetic field, and if you rotate it, due to rotation, EMF induces, and hence if it is having some resistance, current also induces. But in case of bulk conductors, these induced currents will be in the form of whirls. So if you take a bucket of water, if you take a finger or a hand and if you rotate the water, the whirlings will appear like that. The induced currents will appear in case of bulk conductors. These, what is that? Induced currents in bulk conductors which are in the form of whirls are called as eddy currents. Is it clear? So in simplest way you can say the induced currents produced in bulk conductors in magnetic fields are called eddy currents. So write down. What are eddy currents? The induced currents produced in bulk conductors when they are subjected to change in magnetic flux. So in bulk conductors, okay? This is specifically related to bulk conductors. They are called eddy currents. Got it? So this is briefly about what are this what you call induced currents related parts. about the inductance, self and mutual inductance part, we'll discuss in the next session. Okay.